Hi, my name is James Doran and welcome to my video documentary displaying the outcome of my procedural generational content. I'm happy to show the current progress of what I have dubbed Terrain Walker. As suggested by the title, the two procedural algorithms implemented in this project are demonstrations of terrain generation and procedural animations. It was decided these two procedural contents meshed well together. The procedural animations allow for responsive and environmentally interactive player characters to explore the generated world. The project was born through experimentation with generating meshes in Unity. Starting with the creation of a simple mesh with randomized height values, it was noted that, to create more complex and cohesive representations of terrain, more complex methods were required. Perlin noise is a gradient noise that produces normalized values, which can be used to generate smooth, flowing terrain. By projecting these values as height maps, we can create more coherent and natural-looking landscapes. Within Unity, a custom terrain generator script was attached to an empty game object. This script contained the information required for generating vertices in a grid and applying these to a mesh. During the generation of these vertices, the normalized x and z coordinates were passed through Unity's inbuilt mathf class function, mathf.perlinNoise. This function returns a normalized height value based upon where the coordinates passed in fall on the perlinNoise plane. This height value then was multiplied by the desired maximum height to produce a value that applied to a vertice's y-axis. To provide further expression of the height values on the terrain mesh, a method was created to generate a texture that mapped out in line with the mesh's vertices. For each vertex-aligned pixel on the texture, an interpolated color value was applied, normalized through the maximum and minimum height values of the mesh. However, only having two colors applied to the mesh did not produce the variation needed for sufficiently different terrain generation, so a new method was devised. Instead of applying an interpolation between two colors, Unity's gradient class was used to apply its blended colors values across the mesh. This allowed up to 8 colors being interpolated at custom height values. To allow for the generation of large terrain, it was deemed necessary for multiple meshes to be generated. This required the calculation of multiple meshes correctly positioned in layers around the center mesh, regardless of the grid size and spacing of each mesh. Furthermore, the projection of perlinNoise onto the mesh's height required proper calculation to maintain cohesive flow across multiple meshes. The mesh generation code was split into 3 scripts to improve modularity: Terrain Information, Terrain Object, and Terrain Manager. Terrain Information is a non-mono behavior class that holds the input data for mesh generation, like grid size and height parameters. Terrain Manager uses a global terrain information variable to store terrain settings and a list of generated meshes. When settings change, it recalculates positional and Perlin offsets for each terrain tile to ensure cohesion across seams. A loop generates new terrain object instances, passing adjusted terrain information into each. Terrain Object handles local terrain generation. It takes the input parameters from Terrain Manager and applies positional and Perlin offsets to create local meshes. To generate multiple tiles, the Generate Positional Offsets method in Terrain Manager calculates positional offsets and perlinNoise offsets. These ensure height values align seamlessly across meshes. Each tile is created as a new game object with the Terrain Object script attached, which processes the mesh generation locally. While the process spaces terrain correctly, issues remain with the Perlin offset calculations, causing visible seams between tiles. Further work was to be done. Building on the previous single-layer perlinNoise, I implemented fractal purling noise, which uses multiple layers or octaves to add finer details to the terrain. Each octave adjusts the height using persistence to reduce amplitude and lacunarity to increase frequency, creating more realistic and varied landscapes. Inspired by Lague's tutorial on procedural landmass generation, I processed each vertex through all octave layers, summing the heights to produce the final value. The result is normalized to fit within the terrain's height range. This normalization ensures seamless blending across layers. To further enhance variability, I integrated animation curves. Before applying Y values, these are evaluated against the curve, allowing for terrain customization such as flattening valleys or accentuating peaks. Seams between neighbouring tiles were a challenge, caused by inconsistent purling offset calculations and height normalization per chunk. The solution involved pre-calculating the maximum and minimal possible heights across all octaves for the entire terrain. By normalizing heights globally rather than per chunk, the seams now align perfectly. Inverse kinematics is a method for animating movement by calculating joint rotations based on the desired position of an end effector, like a foot or a hand. For this project, I used the fabric algorithm via the FastIK Unity asset, which efficiently calculated realistic joint movement. Each limb of the walker is structured as a hierarchy of joints, with the end effector controlled by the FastIK fabric script. This script takes input for the target position, which the limb moves towards, and an optional pole to influence joint bending direction. The walker uses procedural steps based on ray-casted target prediction. Emitters on the body cast rays diagonally forward and down to predict step positions on uneven terrain. These positions are represented by green spheres. When the distance between the current target, the red sphere, and the predicted position exceeds a threshold, our coroutine moves the target smoothly to the predicted position using linear interpolation, lerping. As the target moves, the corresponding limb adjusts dynamically using the IK system. The walker body stays offset from the terrain, where its height and position averaging the leg placements. Key parameters for the procedural animation of the walker include its stride length, controlling the step distance for each leg, the step speed, adjusting the lerping time for limb movement, and the body offset determining how far the body is raised above the terrain. Implementing an animation curve for the leg arcs caused clipping issues on uneven terrain, so it was disabled. Additionally, handling more complex surfaces sometimes resulted in minor clipping of the legs or the body.